Today we're going to look at graphs of trig functions again. We're going to look at sine and cosine and then develop some theories about what it means to translate them. So up, down, left, right, and then stretched, and talk about things, new words, new vocabulary, amplitude, period, phase shift. These are all varieties of translations. So I want to first talk a little bit about just sine and cosine again. You've graphed them. We graphed sine in class. You graphed cosine for homework. And I just want to repeat, y'all did a great job of answering the questions that went with that assignment. You noticed a lot of great things. Sine and cosine have the same shape. They have the same range. So let's just review. So this is a function y equals sine of x, and it gets graphed on the xy plane. The values for sine come from the unit circle, but they get graphed here where we look at 1, 2, 3, 4, 5, 6. This is a little bit more than 6. Sine goes through 0, 0, and it also goes through 0 at pi, which is 3.14, which is about here. So I want to connect the idea that although I can do this in pi's, this is 2 pi, and this is pi, these are still just regular numbers on your XY chart. And the highest it goes is 1. So if this is 1, this is about 1, this is about 1. So this is -1 and +1, and at pi over 2, that's somewhere here in the middle, sine goes to +1, in the middle over here it goes to -1, and sine is curvy, so it goes around, it goes down, this is almost a straight line in between, and then it curves slightly and goes back up, and this is one period of sine. And I want you to be able to sketch that pretty easily. Sine starts at, I'm going to say starts. It doesn't start there because it's periodic. It goes backwards forever, so it also goes this way and goes down to 1. Shouldn't go below 1. And it comes back to 0 and has this basic shape going this way, and it continues this way. But we get all the values of sine from the unit circle, and this, starting at 0 and doing a positive curve, and then coming down and doing a negative curve and coming back to 0, this is one period of one period of sine. So this is called period. For sine, we have a 2 pi period. Which that simply means that if you're looking at the unit circle as a reference, you started here at 0 and you went around one time and you got back to 2 pi, which is here. And these are all the values of the unit circle graphed here, stretched out like you had a fruit roll up and you unrolled it. But if you go around the unit circle again, you would continue on this cycle, or if you went backwards, you would have the same graph go this way. But this is one repeat. This is like one repeat of the pattern. And all trigonomic functions have a pattern. So sine has a pattern, cosine has a pattern, tangent, cosecant, secant, cotangent, they all have a particular pattern, and while they can look similar to each other, sine and cosine look similar, they all have particular values that will be clues about what they are. So sine starts at 0, 0. So I want you to keep that in mind. Okay, so we've talked about the word period. This represents one time around the unit circle. I don't know what I'm writing. Around the unit circle for our like XY chart. It represents one repeat of the pattern. Then we have another word, it's amplitude. And amplitude is how big the wave goes up or down. So in my sine graph, which is graphed up here, if I do a red center line, I'm going to call the red dotted line, I'm going to call it the midline. The amplitude is how far up our function goes. This one is going up or down 1. Sine and cosine. The parent function has amplitude of 1. And you can see that above, I've got a midline, and the graph, although it goes up and down, it only goes up 1 and it only goes down 1. And that's part of from the range, it's like half the range. So this, the parent function for sine or cosine goes from -1 to 1. That's 2, and half of that is 1, or the amplitude of 1. And we're going to play with that today with some different graphs. The last thing that we look at is phase shift. And phase shift is like a left-right translation. Left-right translation. And when I ask the questions about sine and cosine, many of you notice that sine and cosine are the same graph. They're just moved. So they go to the same places. They go to +1 and -1. They just happen at different times. And so I want to graph for you real quick here on Desmos. So let me pull up Desmos. I'm going to turn that one off for a second. Okay, so if I graph y equals sine of x, there it is. I'm going to make it a little bit larger for now, if I can. There we go. Okay, so y equals sine of x, and I can't quite, well, here's one period from 0 to 6.28, so 2 pi. So that's one period of it. You can see it right here. That's 1. Here's another, starting at 0 and going back to 0 with an up and a down. Let's graph cosine. Y equals cosine of x. And because I'm on an xy plane, I'm actually plugging in x values, which is a little bit confusing, but here it is. Now you notice they look very similar. They have the same up and downs. The wave is the same size. Cosine has a period of 2 pi as well. It starts at 0, 1. It starts at 1 on the y-axis, and it goes down to -1 and then back up to 1. So it ends in the same place. So its period looks like a U. And then here's another period where it starts at the top and goes down and then up and starts again, down and then up. That's a period of 2 pi before it repeats again. Okay, but what happens if I type in y equals x plus pi? You can type in pi divided by 2. Look, I've made it so that they're not quite the same amount of shift. And it's a very pretty looking graph, but what happens if I do this? If I say minus, you can't even see that they're separate graphs. I have shifted it a pi over 2, and then they have the exact same values. I have shifted the cosine left, I've shifted it right. Sorry, this is opposite math. So I've shifted it right to pi over 2. So instead of this point being here, it's shifted to the right, pi over 2. And now cosine and sine, even though this is a sine function, this is cosine, they have the same points. It's been shifted. So phase shift shifts it left or right. You can barely see that on my list there. Okay, so we've done a little bit of graphing here and shown sine and cosine. I want to talk about what it means to change period and amplitude and phase shift a little bit. We also have vertical shift. So let me add this to our list. Vertical shift. And the great thing about all of these is that you already know them. You already know how the function gets shifted, and we're going to do some regular functions first and then apply it to sine and cosine. So it moves your graph up or down, and that's pretty obvious, but we'll go through what that looks like. Okay, so if you were able to pull up Desmos, that's fantastic. If you cannot, you can do all of this on your calculator. I just use Desmos because it's easy to show here on the screen instead of a small calculator. So either one is good. So first I want to talk actually about amplitude. I think it's the easiest to see on a calculator. I'm going to graph several things and I want you to see what they look like. So I'm going to graph these things. This is for amplitude. I'm going to graph y equals x cubed minus 4x, and then y2 is going to be 3x cubed minus 4x, and then y3 will be negative 3x cubed minus 4x. Now hopefully right here you've noticed that this is some function that's going to have some shape, and this is the same that's multiplied by 3. So this is a stretch. It should take my graph and stretch it. We already know that. And this one's going to also stretch by 3, but then the negative will flip it over. So let's just look. Those are things you already know. Let's confirm it by graphing. So I'm going to turn this one back on by clicking here. There's my function. For the second one, I'm going to take the same thing. I need to put parentheses so that my 3 will do this job correctly. And I'm going to put 3 in the front. Voila. This graph is stretched. It has the same zeros, but the whole graph is stretched up. And then for the third one, I'll copy this one because it's very similar. And if I put a negative in the front, I'm going to turn this one off so you can see it. If I put a negative in front, it graphs the same stretch, but it's flipped over. So what was a maximum is now a minimum, and what was a minimum is now a maximum. So that's stretch. Let's apply that to sine, okay? Feel free at any time to pause the video so you can plug it in the calculator and do it yourself. All right, so I'm going to pause the video real quick and write some notes, and then I will come back and we'll look at sine. All right, so now I'm going to graph sine. Sine of x is up here on Desmos. I've changed my setting right here, and I put it in pi, so steps in pi, just so I can see the period really easily. From 0 to 2 pi is the period for sine. And then we're going to do the same thing. We're going to do a stretch factor in the front, so y equals, and I have right down here the 3 I'm going to graph. 3 times sine, and you can put it in parentheses or not, but it has the exact same zeros. 0, 0, pi, and 2 pi, 3 pi. At every pi, sine is 0. And then it has a maximum at 1. That's the top of the unit circle. That's why sine is 1 here. It's at the top of the unit circle, and it's the y value. And this one is going to be 3, which Desmos, I can point at it, and you can see it pretty easily. So pi over 2 is 3. The value, you plug in pi over 2 into your unit circle. On the unit circle, pi over 2 right here is 0, 1. So the sine value is 1. You multiply it by 3 and you get 3. And that's why this maximum is at 3. It happens again at 5 pi over 2. That's the second revolution around the circle. Anyway, it's been stretched by 3. The number on the outside is a stretch, just like with absolute value, just like with this polynomial function. And then hopefully you can guess that y equals negative 3 sine of x is flipped over. So here's the normal sine function, has a maximum at the point pi over 2, 0, and pi over 2, 1, sorry. This one is positive pi over 2, but it goes to negative 3. So you plug in sine of pi over 2. Pi over 2 is the input value. And then you get positive 1. You multiply positive 1 by negative 3, and here's a point negative 3. So it has stretched the graph, and it has flipped it over. Stretch and flip. So I'm going to add this to my notes, and then we're going to look at the other things we have in our list. Phase shift, vertical shift. Also, the midline for this function did not change. It's right here in the middle. We can actually talk about amplitude. The amplitude for this is 3. The amplitude from the midline up is 3. So I'll write that down. Here are my notes. I'm going to graph it. I've got regular sine looks like this. The stretched function looks like it goes from 1, 2, 3 through the same 0, 1, 2, 3 through the same 0. This is the midline in the middle. From 3 to negative 3 is 6, but the amplitude is 3. It's this distance right here, 3. And it's the same number that's in the front, so that's convenient. It would also be 3 for this function, but it's just flipped over, so your maximums and minimums are switched. So we've talked about two things here. We've talked about the stretch, and that the amplitude is the number multiplied in the front, so amplitude. These functions have the same period. Nothing got changed with period. We will do that next. All right, I'm going to pause and reset. Next, I want to talk about vertical shift. Vertical shift happens on the outside of a function. So I've got y equals sine of x graphed on Desmos and on my paper. I'm going to graph y equals sine of x plus 2. It takes the same graph, the same shape, and it shifts it up 2. So y equals sine of x plus 2. This is a vertical shift, so instead of starting at 0, it's going to start, this is 1, because that's here, 2. It's going to start here. So it's going to go, have the same, here's my, if it goes up, it's going to go down to 1. This is, there we go, up and then down. My midline is here and up. Here's the period. All right, so that's hard for me to graph looking at all these different things, but it shifted up 2. Everything is up 2. This is up 2. This is up 2. This is up 2. But the midline here, this is the midline of the red function. It still has an amplitude of 1 because there's an understood 1 there. Amplitude equals 1. So it has a vertical shift, amplitude up 1. So the next thing I want to talk about is period, and I want to remind you what it means to be inside the parentheses. So this is going to be a new part here. This is going to be period shift. So the parent function, y equals sine of x, has period 2 pi. Period shift happens inside the parentheses. So for example, if we say 3x here. This 3, it changes the period, but not by multiplying by 3. It changes the period by dividing by 3. It is opposite math. And this is important. It is opposite math because it's in parentheses with x. This is the same thing when we do zeros and we say x minus 2. So 2, positive 2 is a 0. Same thing. So changes period with opposite math. The period equals 2 pi divided by whatever the number is. I'm going to say multiplied by x in parentheses. So let's look at it. Here is y equals sine of x. Here is y equals, and this is where the parentheses become important when we actually change the argument. So 3x is in green, and can you see it? It's squished. It didn't multiply by 3 and make the period bigger. It didn't stretch it out. It shrunk it. It's opposite math. So this is shrunk left to right because it's opposite math. So if you look, this goes up and down and back up, and this is 2 pi over 3, which is what I have here. So this is one period. If I graph it, so here's a normal period to 2 pi, and then 2 pi over 3, trying to take this off, 2 pi over 3 is not quite here, because that would be 3 pi over 3. So it's 1, 2, there's your thirds. It's going to go up and down and back to here at 2 pi over 3. 2 pi over 3. Shrunk. Notice how the amplitude is still 1. Notice amplitude is still 1. Because y equals sine of 3x has amplitude equal to 1. That's sort of sideways. And then this is period change. It's always going to be 2 pi divided by the number multiplied by x. So in this case, 2 pi over 3. We could take that whole thing, we could shift it up. Let's say plus 4, and look at move the whole thing up. We could say minus 4, that's vertical shift. We can say right here in the middle and then close this one off for a second to look at it. It has an amplitude of 1, and the midline is at y equals 0. It's right in the middle. You can see amplitude of 1 here and amplitude down of 1 there. Okay, so let's take this whole thing and multiply it by 4. Now it has an amplitude of 4. The midline is still 0. It goes 1, 2, 3, 4, and then down 4. So we're looking at amplitude and period shift. Let's see what happens when we make it bigger. So if multiplying by 3 makes it smaller, we need to multiply by a fraction to make it bigger. So let's make it doubly as big, which means we're going to put in 1/2 here. So now the period, I'm going to move this wider so you can see. That did not help. There we go. Instead of going to 2 pi with 1 up and 1 down, it went to 4 pi. So let's look at that as a separate graph. Still period shift. And we're looking at y equals, I'm going to take the 4 out. There. Y equals sine of 1/2 x. This has an amplitude of 1. It has a period shift of, usually it's 2 pi, that's standard, divided by the number multiplied by x. So divided by 1/2, that means we're going to say 2 pi times, flip this over, 2 over 1, and we get 4 pi. The period is 4 pi, and normally it goes to 2 pi like this, and this one now goes all the way to 4 pi. Oops, it's not taller. My bad. There's a tendency to make it want to be taller, but it's not. There we go. And it goes like that. So it still has an amplitude of 1. I needed to show that 1. But it ends here at 4 pi. So it's opposite math with period shift. Opposite. And that's always been true in parentheses with x. So same idea there. So we've talked about vertical shift, amplitude, vertical shift, and then phase shift is just like when we saw for zeros with x. It's opposite math. I'm going to do one example of that, and then I know you're done with me because it's been a long video. So pause one more time. I'm going to reset. Okay, last thing. Phase shift moves your function left or right. Left or right. So let's take a quick look at something easy. Y equals x. I'm going to use the caret symbol. It takes me up to squared. Y equals x squared. Remember that if you put in parentheses, so if you say minus 2x squared, it shifted it not to positive 2. I'm sorry, not to negative 2, but to positive 2. So it's opposite math right here. If you say minus 4, it'll shift it over to 4. I'm going to change this back to numbers. So here we are at 4. If you change it to plus 3, it'll be at negative 3. So it's opposite math. So the same thing happens with sine. If you say sine of x, you're here. But if you say, and you change your argument, everything in parentheses, x minus 2, then instead of starting at 0, it starts at 2. So left or right, shift. It is numbers plus or minus a number. So like x plus 2 is left 2, and x minus 3 is right 3. So this is changing the argument, and it is a composition of functions. So if we have y equals sine of x, it goes from 0 to 2 pi, that's one period. But if we change to y equals sine of x minus 2, that means right 2. And so my function, which should be starting at 0, now starts at 1, 2. So it's going to go up and down and end at a different place. It's going to end at 2 pi plus 2. 2 pi plus 2. And this is 2. So this one has a start at 0, 0. And this one has a start at 2, 0. So that is phase shift. And that's what I did earlier with the cosine adding pi over 2, was I gave it a phase shift to make it match up with sine. All right, back to me. So page 518 in your book, it gives you this beautiful summary section. It says, okay, let's define where the amplitude and the phase shift and the period all come from. And so I've written down a summary. You can see on my paper, f of x equals a times sine, and in the parentheses is the composition of functions, bx minus c. Same thing for cosine. They have the same sort of translation. So let's first confirm what we know about the parent function. The amplitude is always 1 for the parent function. The period is 2 pi in the parent function. They start at 0, 0 for sine and 0, 1 for cosine. That's our starting place. And there's one more thing, the midline. The midline for both of these functions is y equals 0, and that could be shifted up or down if something's added or subtracted to our function. So those things are standard, and then when we have a shift, then we start to have changes. So in our functions written here, a times sine of bx minus c, they've got right here written out, and then they have it all described. So a equals amplitude, and that's the distance from the midline. Does that all show? Yep. Okay, and then B is where we get our period. So B goes with period. That's that number multiplied by x. So we're going to say that period equals 2 pi, that's standard, divided by B because it's opposite math. And then in red, I have minus C. That is, that's phase shift. C defines phase shift. And sometimes because we have this period shift, you'll see phase shift is actually equal to C over B. And we'll do some problems where we factor it out. You can see where that comes from. But the phase shift is managed with taking that opposite value, opposite math here, but you also have to divide by B. So it looks like if you were to factor it out, B times X minus C over B. And that's the C over B right here. So this part of the composition of functions, if you factored out, this tells you about the period, and this tells you about the phase shift with opposite math. And then one thing they didn't talk about, but it looks like I'm going to write it out like I do when I do absolute value functions, is if you were to add a k value to the end, that would tell you where your midline changes. So k defines up or down of your function, and it moves the midline. So if you had plus 4, then your midline would be at y equals 4. Okay, so you've got some homework to deal with for this section. I've tried to cover everything, and I've covered it maybe too much. You can definitely read about this in the book. Go up to page 518. Tomorrow we will graph the different functions, tangent and cotangent, and then cosecant, secant. So we're really just focusing on period, amplitude, phase shift today for sine and cosine. They're the most used periodic functions, the trig functions. All right, thanks a lot.